Okay, so we're going to start a short unit that is a nice tie between differential calculus and integral calculus. So let's talk about what is a differential equation. Very simply stated, it's an equation that contains at least one derivative of some function. Here are a few examples. dy dx equals 3x squared, where you see the derivative of y is explicitly stated over here. Dy dx equals x plus y, where the derivative of y is over here, and you have a function of x and y on the right side. And then this example right here has actually two derivatives, the second derivative of y and the first derivative of y, and also you can see functions of x and y mixed in. Okay, differential equations are very complicated. This is a whole course taught in college. Once you get past calculus 3, we're just going to look at one small family of differential equations in this unit, just to kind of introduce you to the concept. Let's talk about what a solution to a differential equation is. Okay, there are two types of solutions. There's a general solution. A general solution is a function that makes the equation true. And because we know that when you take an integral of a function, you have to have a plus c, or in other words, there are an infinite number of functions that have a given derivative, a general solution will have a plus c involved. Okay, we've seen some basic differential equations already, and we could solve this one here by hand. We know that the function or family of functions that has the derivative dy dx equals 3x squared would look like x cubed plus a constant. Okay, so this is a family of functions. We would call this the general solution because of the plus c. This is not a single equation. There are many equations that have the derivative 3x squared. Then we have what's called a particular solution, and one of the key facts about differential equations is that under the right conditions, a differential equation and initial condition will only have one solution. So if I say that some function has the derivative 3x squared and passes through the point 0,3, there is only one answer to that problem. So key definition here that you're going to want to write down because it's going to come up a little bit later. It says a particular solution to a differential equation is a differentiable function defined on an open interval that satisfies the differential equation and passes through the given initial condition. So in this case, I need a function that's differentiable on some open interval that has derivative 3x squared and also passes through the point 0,3. This one's simple enough to solve by hand because we know that functions that have the derivative 3x squared will look like x cubed plus c. And we can solve for the c because we know that the function goes through the point 0,3. So 0 plus c equals 3, so the c has to equal 3. So the function we're looking for is x cubed plus 3. That is differentiable for all real numbers. And so the domain for this guy would be all real numbers. We'll see some issues with the domain coming up a little bit later. Okay, one of the things you're asked to do from time to time is to verify that a function is a solution to a differential equation. So we'll take you through two examples here. The differential equation given is dy dx equals x plus y, and we're to show that both of these functions, y equals negative x minus 1 and y equals negative x minus 1 plus 3 e to the x, are solutions to dy over dx equals x plus y. Solutions means makes the equation true. So that's what I need to show. They're telling me, hey, this works. Show me why it works. So I need to show that this function will make this differential equation here true. So it says dy dx equals x plus y. So the dy dx, or the derivative of this equation, would be negative 1 minus 0, or just negative 1. And so when I plug things back into the differential equation, I need to show that both sides are equal. So dy dx is equal to negative 1 is equal to x plus the y that we have over here. So y is equal to negative x minus 1. So if I plug that in, I should get a true statement. Negative 1 is equal to negative 1 because the x's cancel. Okay? So there you have an example of a function that satisfies the differential equation. This function over here should also satisfy the differential equation. So let's see if that's true or not. Here, dy dx will equal negative 1 minus 0 plus 3 e to the x, or just negative 1 plus 3 e to the x. And so when substituted into the differential equation, we should get a true statement. So negative 1 plus 3 e to the x is equal to x plus the original y, which was negative x minus 1 plus 3 e to the x. And when I simplify this, the x's cancel, and I have negative 1 plus 3 e to the x, and that was equal to the left side of the equation. Okay, so two different functions that satisfy the differential equation. We know that there are an infinite number of solutions because of the plus c, and there are two examples. Okay, so now let's play a little game of what if. So let's say you were told that a function has a derivative equal to negative x over y, and it also passes through the point 0, 2. What do we know about this curve or this function? Well, if I go over here and I plug in x equals 0 and y equals 2, I'm going to get negative 0 over 2 or 0. So this tells me that at the point 0, 2, the slope of the curve dy dx equals 0. Okay, what does that mean? That means if I zoomed in on the curve, I would see a dot at 0, 2, and the slope would be flat because it would have a slope of 0. So zoomed in, you would see this picture over here. Horizontal tangent line at the point 0, 2. And so what that means is if you zoomed back out, you would see a curve that appeared flat for an instant when x was 0 and y was 2. So something like this picture over here. So that's not terribly descriptive or helpful, but it's some piece of information that we can deduce from what we've been given. Okay, now let's say at a different place, at this point square root of 2, square root of 2, we had the same slope, same differential equation. What can we figure out from this? Well, if I plug in square root of 2 for x and square root of 2 for y, I'm going to get a slope of negative square root of 2 over square root of 2, or negative 1. So at the point square root of 2, square root of 2, I know that the slope of the curve is going to be equal to negative 1. What that means is when I zoom in on the point square root of 2, square root of 2, I should see a line that has a slope of negative 1. And when I zoom back out, my portion of my curve would look like a line with a slope of negative 1, which is what I see here. Again, that's not a lot of information, but it's something. And when you combine a lot of somethings, you start to get a pretty descriptive picture of what's actually going on. So here I plotted a lot of what ifs. And this picture reveals to us what kind of curve or curves, what family of curves has the derivative dy dx equals negative x over y. Okay? And you can kind of clearly see that these curves appear to be circles that all have the center of the origin and have different radii because of the plus c. And so this picture can help us determine what the solutions look like, even though we may not be able to actually solve the differential equation for y. Okay, this picture is called the slope field. So just so you have a definition, a slope field is a graphical representation of the family of solutions to a differential equation. Okay, so this represents a family of solutions to the differential equation dy dx equals negative x over y. You are seeing portions of the curves because we've been graphing just line segments to represent pieces of the curve. So one of the things you're asked to do from time to time is to sketch a slope field. You don't have to sketch very many points, but they want to make sure that you have the gist of what's going on with the slope field. And then you're asked to interpret a slope field by looking at its picture. So let's go ahead and sketch one. So they will give you what are called lattice points on a grid. So these are the points they want you to draw slopes at. And the differential equation given is dy dx equals xy. Okay, so I'm going to do a couple. Then I want you to pause the video. I want you to fill in the rest, and then we'll compare our final picture. So there are a couple easy points to start. Dy dx equals x times y. Let's plug in the order pair 0, 0. That's one of my lattice points, and it's very clear that the slope at 0, 0 will be 0, so I can draw a flat or horizontal tangent line right there. In fact, anywhere where the x-coordinate or the y-coordinate is 0, you'll have a slope of 0. So I can go ahead and fill in all those right away. Okay, and that's a nice little feature about slope fields is that once you hone in on some patterns, you can start to get a bunch of slopes real quick. Okay, and I'll do one more. Let's do the point 1, 1. All right, if I plug a 1 in for x and a 1 in for y, I'll get 1 as the slope. And so I need to draw a small line segment that has a slope of 1 at the point 1, 1, which is right here. Okay, you don't have to be terribly precise, but I have a ruler just in case I need to draw some slopes that are steeper than I expect. Okay, so go ahead, pause the video, fill in the rest of this, and then we'll talk about the rest of it when you're finished. Okay, so that's basically what you would see when you finish your slope field. What they're looking for are slopes that are positive versus negative. You should be able to tell those from your picture. You should also be able to tell slopes that should be steeper. So the slope at 2, 1, you should have steeper than the slope at 1, 1. They'd expect to see that. They'd also expect to see 0 slopes where they are appropriate. From this slope field, you might say that the function either has a max or min at x equals 0. And as I look at this slope field, I think this slope should be reversed like this. There we go. You could also say possibly that the function has a horizontal asymptote when y is equal to 0. So depending on what kind of curve we have, that's also a possibility. To make your slope field more accurate, or to make it more descriptive, you would make your points closer together and include more points like I did in the previous slide.